the nucleus can have a dipole moment depending on the number of protons and neutrons that are within that nucleus. So if it's an even number, no, it will not. But if it has an odd number, similar to the proton, then you are in a unique situation for it to have a magnetic moment. But that magnetic moment is much weaker than the electron moment, because essentially moments are caused by charge, essentially. So they're directly correlated to charge. Nuclei are essentially randomly aligned, but not truly, because we all are exposed to a magnetic field. The Earth has a magnetic field, and therefore the alignment is similar to a compass, that they are essentially aligning in a more random association, but aligning parallel and anti-parallel. The number of nuclei that are aligning parallel and anti-parallel are directly associated with the strength of the magnetic field. So therefore, if you have a stronger magnetic field, you have more protons. In this case, we'll sort of just talk about protons, but the effect is similar to and is always the same, depending on whatever nucleus you're talking about. Just the frequency is different. That all being said, the number that are aligned parallel or anti-parallel are directly correlate to the magnetic field strength. And the magnetic field strength is in units of Gauss or Tesla. So 1 Gauss is the field strength of the Earth. At Tesla, 1 Tesla is 10,000 Gauss. So in most magnetic field strengths that are clinically relevant are 1.5 Tesla or 3 Tesla. So therefore, the magnetic field strength of a normal clinical MRI is about 15,000 times the field strength of the Earth. So you could, in theory, image something with the Earth's field strength. It would just take a very, very, very long time. What is a spin? Well, I mean, I guess the confusing aspect of MR is that you can actually look at it from a quantum mechanical standpoint, and that's where this parallel and anti-parallel makes perfect sense. Most people kind of go from these, and the reason why that is the case is that all the nuclei are not statically pointing up or pointing down. They're actually like a top. They're spinning around an axis, and therefore they're spinning with their nuclear magnetic moment parallel or anti-parallel. The traditional MR physicists then translate themselves into a Newtonian way, going into that imagining yourself sort of in an Einstein way, that you're actually traveling with the car. You're putting yourself in the perspective of the nucleus. So you put yourself in the rotating frame, right? So then you're static and the rest of the world is spinning around you. So then you're in the rotating frame, and then you sum up all of the vectors of all of the protons that are spinning parallel, and that's your magnetization vector, and that's the total amount of magnetization that you could potentially get as signal. So spin is kind of what the protons are doing, but then you're exploiting those spins and that energy difference to get your image signal. And each nucleus is spinning either parallel or anti-parallel, and so therefore, and the energy difference between the parallel and anti-parallel state is directly correlating to the field strength, and it's all governed by an equation called the Larmor frequency. And the Larmor frequency is a simple equation that relates the frequency to the gyromagnetic ratio. In this case, the gyromagnetic ratio of a proton is 42.57 megahertz per Tesla. So then if you multiply 42.57 times 1.5, you get the resonance frequency of protons at 1.5 Tesla, which is 63.9 something. And it's very close and very homogeneous. So the key to an MRI is having an extremely homogeneous magnetic field within the center of that large MRI machine, so that in something that almost looks like an eggshell, right? Actually, an egg, a spherical ellipse, or sort of an ellipsoid. You have something that is that is within parts per million. The magnetic field strength varies very minimally within that ellipsoid. What happens to the energy difference as you increase field strength? The energy difference will directly increase in a linear fashion. So as you increase field strength to 3 Tesla, then your Larmor frequency will increase by a factor of 2 in this case. And what happens there is that since the energy difference increases, then the number of spins that you have that are parallel versus anti-parallel increase, and then your magnetization vector potentially increases, so your field strength directly impacts your signal and the amount of signal that you can receive. Put current around a coil of copper, depending on the direction of the current, it will form a magnetic field given the right-hand rule. The polarity of that, the axis of that field is directly relating to the current of the current of the electrons going around, and therefore, the more current that goes through that magnet, through those coils of copper, essentially, the higher the field strength, depending on the geometry and the amount of true copper and coiling that there is. You need the resistance associated with that, and the amount of current associated with that, therefore, gives a lot of heat. So therefore, to be able to make that efficient, you need to bathe that in liquid helium to then make it a superconducting system. And then, in addition to that, to make it essentially to reduce the resistance and reduce the heat loss. And then, since liquid helium is at 4 Kelvin, you need to bathe that liquid helium in another bath of liquid nitrogen, and then go to air, so that you don't have heat loss at various capacities. So you go from 4 Kelvin to whatever liquid nitrogen is, 120 something Kelvin, to then air.